Hey, BC Calc, this is your day 18 notes. Today we're going to be talking about linearization a little bit more and talking about the concept of differentials. And there's a very close connection to these two concepts to get you in the mindset of what we did with linearization in the prior lesson. We'll recall that the formula for L of x is f of a plus f prime of a times x minus a, which this is basically just the slope of the tangent line, or the equation of the tangent line rather, at x equals a. So see if you can use our ideas with linearization to find the linearization of y equals cosine x at those values x equals 0, pi over 2, and pi. It might be nice to kind of sketch a graph of cosine x and the linearization at those values, just as a quick confirmation there. So go ahead and try that. We will go over that next time I see you in class. But if we go ahead and take a look at the bottom here where it says estimating change of differentials, the question is, well, if we change x by a certain amount, how much does y change? And we can use tangent lines to help us approximate this, but it's not going to be an exact amount, just like we did with linearization. So we're going to approach this in a slightly different format today, but it essentially amounts to the same thing that we were doing with linearization. So I have a diagram that I would recommend at this point in the lesson, hitting pause, to get this diagram into your notes. Okay, so I'm going to talk through the diagram, which is why I think at this point, if you hit pause real quick, copy it down, and then I'll kind of describe what's happening here. So like I said, my question here is if we change x by a certain amount, you can see the change in x here represented by delta x. How much is y going to change? So in this diagram here, we have the curve y equals f of x. We have this red tangent line drawn at our value of x that we've selected. And if you were to find the slope of the tangent line, that would be dy dx. What we'll say is that delta x, the change in x, is approximately equal to dx for small changes in x, right? If we don't go very far away from this value, even though the picture might be a little exaggerated here, if we're trying to find the value on this function that's pretty close by, we can say that delta x is equal to dx for that. But you'll notice that when we go to talk about the y values here, delta y is going to be the change in total by moving over delta x. But dy is only the change up to the tangent line. So we do have a little bit of error that we have to squeeze in there. It's not going to be an exact value if we use the slope of the tangent line, but it is pretty close, isn't it? So we know that the slope of the tangent line is dy dx. We know the slope of the secant, according to this, would be dy dx. So what we'll say is that since there's just a little bit of error based on that change, we're going to say that the change in y for the secant line is approximately what the change in y is for the tangent line, which you can see we've represented in this case as dy, and that's the differential. Okay, so as we change a little bit in our x value here, we get that dy, the differential there, is going to approximate the actual y value on the curve. Okay, and we can calculate what that error is fairly easily, and we'll do that in some examples today. So how are we going to figure out what dy is equal to, what that differential equals? So if you go to the next page, we have that dy over delta x is equal to the slope of the tangent line, f prime of x, and you can confirm that by looking at our last picture. So then dy would equal f prime x times delta x if I multiply the delta x to the other side. And since delta x and dx are the same for small changes in x, we have that the differential dy is equal to f prime of x dx. And hopefully this is making sense that this is really the same idea as linearization. It's the slope of the tangent line at x times that little differential change in x. Okay, so the question off to the side here, so when we change x by delta x, how will the y value change? That's exactly what's happening right here. Okay, the change in y should be approximately what dy is, which is going to be equal to f prime of x dx. So to estimate the new y value on the curve, we'll take f of x and we'll just add on that dy, and that should be a relatively good approximation as to what the new y value is for the curve. So in general, delta y is going to be approximately what dy is, which is f prime of x dx. Let's put this into practice. If we want to approximate 4.98 to the fourth, how are we going to do that? Well, let's think about first what function would best model approximating 4.98 to the fourth. And since it's a function of where we're raising something to the fourth power, I think it makes sense to consider that f of x equals x to the fourth. So in order to be able to calculate this, let's do this from an approach of differentials by saying that the derivative, first of all, f prime of x, is equal to 4x cubed. And that this value that we're trying to evaluate, 4.98 to the fourth power, is fairly close to x equals 5. So if we let x equal 5 to be that point that's really close by to x equals 4.98, then we would have that delta x, which remember is our dx in this case. If you subtract those 4.98 minus 5, that's negative 0.02, right? That's our change in x. And that dx part in this case clearly can be a negative amount. So to figure out what f of 4.98 is, we're saying that that's going to be approximately equal to our new y value, f of x, so that's f of 5, plus dy, plus that differential. F of 5 is pretty easy for us to calculate, right? That's just going to be 5 to the fourth. But the dy, well, the change, that differential, there's f prime of x dx, so it's going to be f prime of 5 times our dx, where we know f prime of 5 is going to be 4 times 5 cubed. And then the dx in this case is negative 0.02. So if we make those substitutions appropriately there, 5 to the fourth is 625. And 625 plus, this actually turns out to be 500 here, 4 times 125, times the negative 0.02, gives you a total here of 615. So using differentials, this concept of taking the actual y value plus whatever that differential is by going back 2/100ths on the x-axis there, we can use the slope of the tangent line to approximate that. And of course, we can then check this on the calculator to see, how accurate we are. And on the calculator, if you type in 4.98 to the fourth, you wind up getting that it's 615.05984, something like that. So look how nicely that tangent line approximated the actual value from the calculator. Pretty close. Okay. So could we have approached this through linearization from yesterday? Absolutely. All right. We have the function f of x equals x to the fourth. Our value of a, we're finding the slope of the tangent line at 5. And our value of x in this case is going to be 4.98. So we're doing L of 4.98. That would equal f of 5 plus f prime of 5 times 4.98 minus 5. And notice how it turns into the same exact thing we just did with differentials. This is f of 5, 625, plus the value of the derivative at 5 was 500. And then this difference here is negative 0.02. So that confirms through linearization, we're going to wind up getting the same results. So it seems like if they're doing the same thing, can we just use one as opposed to another? You do have to be familiar with both concepts, both differentials and linearization, because sometimes the questions will be asked where you're supposed to use one technique as opposed to the other. All right. Let's try another example using differentials. If you take a look at the next page, we have, let's approximate the square root of 9.1. So again, to approximate this, let's think about the function that we can use. And if I'm taking the square root of a quantity, in this case, we're going to use f of x as the square root of x in this case. And to figure out f of 9.1, we know that that's approximately f of 9 plus dy. So we're going to have to find, in order to get dy, we know that's f prime of 9 times dx. So we have to figure out what those two things are. If we apply the power rule for radical x, we know that the derivative f prime of x would be 1/2 x to the negative 1/2, which would clean up nicely to 1 over 2 radical x. You guys can confirm that. And now we have all the pieces that we need to be able to evaluate these, right? F of 9, that's pretty easy. That's 3. Plus the derivative at 9. So that's going to be a total of 1/6 if you plug in 9 down here. Times our dx. And what's dx in this case? Well, since we're doing this at 9, 9.1 is 1 above that. So your dx is a positive 0.1 for our approximation. And this turns out to be 3.016 repeating. And lo and behold, on the calculator, the square root of 9.1 is just about 3.0166. So it's a really nice approximation. Now, remember that our delta x's, our dx's here, we're only going a small distance from, in this case, our x value at 9 to be able to approximate this. The further away we get, the more error we're going to wind up getting. And the less of a chance we'll have an accurate approximation. Okay. So hopefully that makes sense. And here's my quick little sketch of that, by the way, if you wanted to see just from a graphical perspective. Okay, I've definitely kind of exaggerated this here, but between 9 and 9.1, you can see how the slope of the tangent line, how that y value is a good approximation for the actual y value when x is equal to 9.1. All right, here's kind of a different looking example. It says for this one, for y equals x squared, we're going to go ahead and find 3 things. Find delta y, find dy, and then find the error. So I think it actually would help you at this point to look back at the beginning of the notes to see what those 3 things are. Okay, so delta y is the total change in the y values between this value of x and this value of x. Dy is the differential right here. And then the error is this piece up here. So how are we going to calculate error? Error can be found by doing delta y minus the dy. And that's how we'll get what this little error piece is right there. So let's go ahead and apply that to the function y equals x squared. What we just saw a moment ago is that delta y can be written as the difference in the y values between your 2 values of x. Okay, so you can write it initially kind of as like y2 minus y1. What is that second y value? The second y value is x plus delta x, right? So we're adding on that delta x to our original value of x, and we're plugging that into this x squared function. So it would be x plus delta x squared minus y1, which would be just x squared. And we can clean this up a little bit by squaring the binomial to get x squared plus 2x delta x plus delta x squared, with that minus x squared at the end. And therefore, x squared minus x squared cancel. And we get that delta y is equal to 2x delta x plus delta x squared. All right, from there, we found delta y. Next thing is dy. And dy, remember, is the same thing as f prime of x dx. So f prime of x is pretty easy to calculate in this case. It's just 2x for the function x squared. Remember that dx is the same thing as, or approximating it to be delta x. So therefore the dy is 2x delta x. And now that we have the delta y and the dy, we can find the error in our approximation by doing the difference in these. Delta y minus dy. So that's going to be 2x delta x plus delta x squared minus the dy, which is 2x delta x. And you'll see that we can very nicely get that the error in our approximation here is just equivalent to whatever delta x squared is. Okay, so that's kind of a nice little example to walk you through some things that we should be able to easily find and identify using this concept of differentials here. All right, I think we have one more example to walk through. We'll do this kind of together, and then we'll get a little bit more differentials practice next time I see you in class. So in this example, it says the radius of a circle is 10. if the radius is increased by dr equals 0.1. Okay, so that's the differential in the radius. Estimate the corresponding increase in the circle's area by dA. So we want to figure out what's the differential in the area when the differential in the radius is 0.1. Once we've done that, then we're going to calculate delta A and compare with the estimate. So we know for a circle, getting started here, that area is pi r squared. So if we were to find the derivative here, the derivative would be dA dr, right? We're finding the derivative of area with respect to its radius. And we can apply the product rule here by saying that this would just be, this is a constant out front, right? So using the power rule, it would be 2 pi r to the first, or just 2 pi r. And therefore, the differential in the area is equal to 2 pi r times the differential in the radius, if you multiply both sides by dr. And we know this information because we're given that the radius is 10, and we're given the differential in the radius to be 0.1. So if we plug those in, 2 pi times 10 times 1/10, you're going to find out that the differential in the area just comes out to be 2 pi in that case. Okay. So a circle radius 10, increasing the radius by the dr of 0.1 gives you a differential in the area of 2 pi. So then in the next part, it says up here to calculate delta A and compare with the estimate. So delta A would be the difference in the areas. So it would be pi r, you can represent it as the second radius squared minus the original radius squared. So since the differential in the radius is 0.1, we would have pi times 10.1 squared minus pi times 10 squared. And if you find that difference in terms of pi, we're going to get that 2.01 pi is the actual difference in the areas. So you can see how our differentials up here give you something super close to what the true delta A is. So then, of course, you know, in our comparison, we can talk about what is the error then. Okay, the error would be delta A minus our dA. So the error is 2.01 pi minus 2 pi. For a tiny error of 0.01 pi. If we calculate a really quick percent error on this, percent error would be our 0.01 pi over the original area. Original area would be 100 pi. And this, the pi's would cancel, right? 0.01 divided by 100 is actually now 0.01% error. Really, really, really tiny error, which is nice that we can say with a fair amount of confidence that if we're doing approximations with a small change in the radius here, right, that dr value, that is a really good approximation. We can use our dA and confidently say that the new area is approximately going to be 2 pi based on that. Okay. All right, or at least the differential in the area. If you have any questions about differentials, we'll promise we're going to do more practice within the next few lessons, but hopefully you can see the connection that we have to linearization, and let me know if you have any questions.